My name is Emil Knudstrup. I'm from Aarhus University, and I'm here to talk to you about planetary system architectures. And also, just before we get rid of FIAS, I would like to just show you what we can actually do with FIAS. You can see the sort of main collaborators here, but a large portion of this work is also due to the NOD staff. Not only in terms of photons collected, but also in terms of support, both moral and technical, and then of course also just time in general. I mean, a large part of this work here has been carried out while I was here at the NOD. But planetary system architectures, I mean, the most familiar architecture is of course the solar system here. And up until 30 years ago, this was sort of the only planetary system that we knew of. So this formed the blueprint for how we thought planets would form and evolve. And what are the characteristics of the solar system? Well, I mean, it's sort of a neatly ordered system. So we have these planets here, and they are mostly circular, their orbits. And we have the smaller rocky planets close into the star, but not super close. You can see Mercury here is at a distance, orbital separation of 82 solar radii or stellar radii for this system here, right? And then much further out we find these gas giants. So Jupiter is some 1100 AORs away from the sun here. Another characteristic is that we have this tilt here between the orbital plane of the planets and then the stellar spin axis here. So you can see the stars rotating, blue part moving towards us and the red part moving away from us. It's almost flat, but there is a bit of a tilt, right? But what happens then when we go out and look at exoplanets instead? Do we see them at the same separations as the planets here in the solar system? Right? Do they have the same AOR? And the answer is no. The first exoplanet was a hot Jupiter, so a Jupiter-sized planet much closer to its star than our Jupiter is to the sun. And we see a lot of different sizes of planets here on short period orbits. And some of these are actually even evaporating. And you can ask Mia Lundqvist, the chair of this session, much more about that. Right? And what about eccentricity? Like solar system again, very circular orbits for the planets. And of course, again, the answer is no. We see an extremely wide range of eccentricities and some on very eccentric orbits, like above 0.9. Right, host star. I mean, is the sun the only type of star that we expect planets to be around? And again, the answer is no. We see planets around neutron stars, white dwarfs, the whole spectral range, binary systems in them, around them. And I mean, this is just to say that the diversity of these architectures is huge, right? And now to the main point, the quantity of interest here. What about the obliquity? So this tilt between the orbital plane and the stellar spin axis, right? And just to sort of again reiterate on what our program here is called, it's the Planetary System Architectures, and we have used FIAS here to first off characterize and confirm planets discovered by the TESS mission, which Lars also mentioned here. And we also got a bit of help from Lars. He collected some RVs from us, so thank you, Lars. And you can see we have 3 Jupiter-sized planets here. 2 of them are actually warm Jupiter, so a bit further away from their star than this first exoplanet, the hot Jupiter. And that's sort of the first step in our 2-step approach. And the next step is to go in and make some measurements during transit. So you can see here we've used FIAS to measure the system during transit here. And what are we actually looking at here in the bottom right plot here? We're looking at the Rossiter-McLaughlin effect. And the Rossiter-McLaughlin effect is a distortion of the stellar spectral lines during transit. So as the planet is passing in front of the stellar disk, it blocks out part of the light from the star, right? And this leads to a distortion of the spectral lines, and the result is an anomalous RV shift. So as it blocks part of the blue light, the overall signal becomes redshifted, and vice versa for the other part of the disk. And this allows us to measure the projected obliquity by the shape of this curve right here. And the hope is then that by measuring this, we can make some inferences about the origin of these planetary systems. Right, and we have done that for some systems. Here we have a warm Saturn, so a separation of 24 A/R in a circular orbit. And what I would like to do now is to take you around the clock and around the globe. And we start out here with a Bocadillo at noon, and then we measured the obliquity, and we actually used HARPS North here at La Palma, and we found this to be very well aligned. So this circular warm Saturn is in an aligned orbit. And what we sort of concluded from that is that this was either formed in situ or it migrated through the planetary disk. Right, and you can see if I've covered up some things here. So let's get right into it. And what is behind the curtain? Well, we start with an espresso here. It's another warm Saturn, but this time in a very eccentric orbit. And the espresso RVs we got here tells us that this system is misaligned. So you can see the aligned is the dashed line here, and then the misaligned model here is the solid line. So this is contrary to the other circular and aligned, which is sort of a dynamically cold system. This is dynamically hot, eccentric and misaligned. And now I've unveiled the curtains here. This then leads to this other migration pathway, where it is at a given orbital separation and the disk disappears. Then some mechanism, it could be another planet, excites the eccentricity and then also inclines the orbit leading up to this here. So this would be the high eccentricity migration. And also, you know, there's this sort of possible dichotomy. So dynamically cold, that should be circular, well aligned, or dynamically hot, eccentric, misaligned. Right, and you can see there is this thing over here which we want to sort of mitigate and avoid. That is tidal migration. So you can see there's a common pathway for these two to lead up into a well-aligned circular orbit, and that is due to tidal interaction between the planet and the star. But we can sort of circumvent this by either going for planets that are far away, where these tidal effects are negligible, or for stars where this is also negligible, which is dependent on the temperature. So that's why we wanted to go for these warmer planets. Right, okay, so that was the sort of dichotomy of this high eccentricity, high obliquity. But we also have some other systems here, which are even weirder, actually. So for Siesta, we will look at KELT 4, which is a hot Jupiter around a hot star. And you can see I've already spoiled it here, that it's actually in a polar orbit. So instead of being in the plane like in the solar system, it's actually going around the stellar poles. And you can see here our RVs here clearly show that this is a polar orbit. You can see the aligned model that does not fit at all, right? And then this polar model is spot on. I mean, if I were to make some guesses of whether this was common or not 2 years ago, I would probably say this is spectacular, but we actually find a preponderance of perpendicular planets, tongue twister for you there. By measuring the obliquity here, which Markussen can tell you much more about, so instead of just the projected obliquity, we then measure the true 3D obliquity. You can see we actually find that a lot of these systems are aligned. So these are the systems up here on the y-axis. But there is also this band here around the poles where there is a clustering of planets here on these polar orbits. So that's mighty, mighty strange. And of course, KELT 4 is another example of one of those. Right, and now it's time for dinner. And by Danish standards, this is actually a bit late, right? It's not 6 o'clock sharp, so that's very unfortunate. But we have another hot Jupiter and another hot star. And again, you can see this sort of giveaway here that it's actually in a retrograde orbit. Again, the shape tells us that this planet is going the wrong way around the star. So mind-boggling. And I should tell you, these are HARPS RVs, so from La Silla. And we actually have another retrograde system, which is K2-290, where again we have HARPS North RVs and Espresso RVs over here, and also some from the Subaru telescope. And this is a sort of a very, very peculiar system. So it's a multi-planet system. We have a mini Neptune and a warm Jupiter, and then it's in a triple star system. And for this, we measured both obliquities for both planets, and what we found is that both of these are actually on retrograde orbits. And we interpret that as, here is the sort of schematic of the system. So we have the star in here, and then the planetary disk. And you can see the companion out here has then actually tilted this disk here, and when the disk then disappears, this is how it ends up in a retrograde orbit. So the star here tilted the disk, and this is what we refer to as a primordial misalignment. Right, and this is a very special system in the sense that it has these companions out there. Because when we look at other multi-planet systems here for the Beta Barquito, we actually find them to be quite well aligned, and this system, TOI 1130, Judith can tell you much more about that system. It's also a very interesting system, but it sort of follows the more general scheme of these compact multi-planet systems. I mean, it's very similar to the other one. It's a warm Jupiter and a Neptune-sized planet. And here we only measured the obliquity for the large planet, at least so far, with espresso again, and you can see we find it to be consistent with alignment here. Right, so this sort of the kicker is that these compact multis are mostly aligned, and there are only 3 exceptions to this rule so far, and K2209 is one of them. Right, but moving on to the future, we just submitted a proposal last week where we want to expand on this preponderance of perpendicular planets, and we want to look more into this excitation of the obliquity and eccentricity. We want to look into companionship, how do those guys shape the orbits of the inner planets here, and then we want to just discover more planets. I mean, warm Jupiters, and study some hot Jupiter demographics. That's sort of the aim of our future NOT program here, if we are awarded some time. Right, and yeah, I'll leave you with this last slide here, and you can check out the code that we use to analyze the data here by scanning this QR code up here. And yeah, thank you for your time.